welcome to Organometallics 2025. Suichiro in Florida, can you give me a thumbs up if you're able to hear now? Sorry about that technical difficulty. I'm glad we caught that because then the recording of this would have been totally useless and I'd have to re-record it. So that would not have been good. So thanks for pointing that out. In the future, we'll do a quick connectivity and technical check to make sure you're able to hear and see us okay at the beginning. So welcome, everybody. Please get in the habit, as I said, of signing in for those who are attending synchronously in person in California. That helps us keep track of attendance. I'll start by introducing the teaching team. With me is Wenji He and Annabelle Zhang. Hello again. They've already put a lot of hard work behind the scenes to make this class successful and to update the curriculum and update the problems of the day and the course content. And so I'm very appreciative of all of their help and hard work. We'll start just jumping through some of the logistics. So this is, we'll run through the course syllabus quickly. And I'll point out at the outset that there are a few dates that will change in the second half of the class, not necessarily dates or times that will change, but who's speaking when, because some availability of some of the industry guest lectures has changed since I put this together first. But the overall format of the class is, it runs somewhat in an analogy to like language learning. So we start out learning phonetics and grammar in the form of structure, bonding, and then how to assemble words in the form of elementary steps, and then how to stitch together sentences, how to put together catalytic cycles. And so the first half of the class is really heavy on fundamentals, things like electron counting, periodic trends, and then elementary steps. The second half is heavy on applications, so how to stitch together all these different catalytic, all these elementary steps into cohesive catalytic cycles that are useful for organic synthesis practitioners. And interspersed with more core content lectures are guest lectures who can provide a little bit more flavor about how some of the topics we cover in class directly tie into ongoing research efforts, both in academia and industry. And the guest lectures that we bring in, many of them are happy to also end the class with a discussion of career development stuff. And so that's a great opportunity to ask and have your questions answered. Ask questions and have them answered. And you all arrived here on time, so you'll know that the class runs Tuesday, Thursdays, 8:30 to 10. And for those who are taking the class for a grade or pass-fail, participation counts for 5% of the final grade. So please try to attend all the classes, attend in person and synchronously when you can. If you're not able to attend, please let the TAs know in advance so that we can register your absence. If you're just auditing, then of course you're free to come and go as you like and participate synchronously, asynchronously, a mixture. Post all the classes to Canvas, and we'll also post them to YouTube, so plenty of ways to access what we're covering. Annabelle, it looks like the video is a little out of focus. Is there a way to? I don't know, Suichiro, do I look blurry to you? I look blurry to me when I see it in Zoom. Let's see if we can refocus that. Okay, so the grading is pretty self-explanatory. Participation, we have 2 problem sets, the first of which will go live next week. And the capstone project for this class is proven to be popular over the years. It's a Wikipedia project where you pick a topic relevant to organometallic chemistry and you write a Wikipedia article on it so that the end product of the class is shared with the broader community. And we've had a lot of great articles over the years that now are I think, fixtures on Wikipedia, topics like concerted metallation deprotonation, written by Camille Rubel, one of the former class TAs. Reductive elimination was one written by John Gurek, one of my first graduate students, and of course has been edited by the community over time, in addition to things like ugiamine and Buchwald ligands. So this is a chance to spend time doing something that also gives back to the community, and it's proven popular over the years. Even though it is technically and logistically hard if you don't have any familiarity with Wikipedia, we think that it's worth investing that time because then you can be an active member of that community. And then there's a midterm and final, no real surprises here. These will run during normal class time. We typically will block out a little bit more time just because the assessments aren't meant to be time constrained necessarily. So just one more point about the Wikipedia article. We'll provide more details later, but what I would like to prompt you to think about now is potential topics, because as you'll see in only, when is it? End of next week, we want you to have at least have talked to me or the TAs about one or more topics that you might like to pursue. And I realize this is challenging because you wouldn't have covered a lot of material yet at that point. But in any case, we want to get the topics locked in and early on. And if you're struggling finding a topic, we want to be able to help you find one. So that process starts pretty early, so you have time to develop your ideas. And another question that came up last year was, one option, if you find a Wikipedia article that is very skeletal and not well developed, and you'd like to develop it into a more meaningful page, for example, there's a biography of a prominent chemist that's just a stub, and you want to really build that out, then that's a viable path to go. But you just need to get that pre-approved, and then we need to take a snapshot of what it looked like before, so we're able to make a proper assessment. There are 2 textbooks for the class. Over the years, as Organometallics has been taught at Scripps, it's bounced back and forth of which is the official version. But this year, the Hartwig, and I think for the last couple of years, the Hartwig book is the official textbook, and the Crabtree textbook, which is available at the library, is the supplementary textbook. They're organized in very different ways. They're both gems, really, in their own right, but they're very different. And the Hartwig textbook, I think, tracks better with how we structure the class now in 2025. Are there any logistical or administrative points, TAs, that I should comment on? So each day we'll have a problem of the day sheet that will be printed out, and will also be available on Canvas if you prefer doing it electronically. And in that problem of the day sheet, so here's an example from today. We'll cover a few topical problems, a mix of classical examples and modern examples from the literature. And then we'll provide the accompanying references after the class if you want to read more. We'll cover a chemist whose research connects to one of the themes of the class that day, and then have a quote to provide a little spice and flavor. Anything else? I was just at Disneyland last week, so that's the inspiration for nothing more insightful than that for this week. Anything else, TAs? Any questions from the class? Participation, this is meant to be a very interactive class, so the problems of the day and other questions, I'll use this high-tech method of soliciting volunteers to chime in, and we'll do a lot of the problems of the day in this think, pair, share format, where you have time to a minute or two to think about on your own, and then compare notes with one of your neighbors, and then share out with the rest of the class. Okay, if there are no further questions, we'll jump in, and we'll try to cover a lot of ground. I'll start at 8:30 sharp every day, pending some school drop-off disaster, which is, you think I say that jokingly, but yesterday my son managed to open the car door so hard that he dinged a brand new Range Rover that was parked next to us. So that's how I started my morning yesterday. Okay, so let me share the way that I'll run. So we've done this. This has evolved over the years. We have, in the past done chalk talk only, and that creates some problems because my penmanship is terrible and because the camera doesn't render it very well. So over the COVID period, we came up with this format of doing it like kind of chalk talk inspired, but on an iPad, and this seems to work pretty well. And then the nice thing is I'll just share this, what we cover. I'll make a few notes as we go through, and then I'll share that as a PDF, so you don't have to necessarily hurry to jot down every little bit of information. Is this how it's supposed to look? Okay, I'll start talking while Wenji's working on this. So we'll start the class with a 10-minute detour on something that's just tangentially related and near and dear to my heart and near and dear to my colleague Ryan Shenby's heart, the topic of strong inference, or the method of multiple hypotheses for scientific interrogation. No luck, Wenji?
Sorry, just said.
So what we're talking about when we say strong inference is building on the scientific and intellectual traditions of Francis Bacon, who is credited as the first empiricist and developed this system of inductive inference. And this was popularized in the 1960s by Platt, who published a widely read and controversial at the time paper in Science in 1964. And it was so controversial, this is like the equivalent of clickbait, I guess, in 1964, that Science just published the exact same article again the next year to get more clicks, or back then actual purchases of the issue. And Platt in this landmark paper held nothing back, held no punches, and was trying to reflect and espouse his views on why different fields of science were progressing at different paces. And he noted that certain fields and subfields of science, and two that he pointed out at that time were theoretical physics and molecular biology, were advancing very rapidly, whereas other fields were stagnating. And he addressed this head on with this quote: "Scientists these days tend to keep up the polite fiction that all science is equal." And so you can imagine how this was received. And Platt's point was that the fields that were advancing fastest tended to use a system of scientific inquiry that was slightly different than the one you learn as an elementary and middle school student, where the idea is you formulate a single hypothesis, design a series of experiments to test that hypothesis, and then you either confirm or refute that hypothesis. What Platt was advocating for is a system of multiple hypotheses, wherein you first reflect on all possible explanations or models for which that could rationalize whatever empirical observation that is in question, and then design experiments systematically to distinguish among those hypotheses, leveraging the enhanced logical power of refutation by experimentation. The problem with the system of single hypotheses that we grow up as scientists learning is that you become psychologically attached to your pet hypothesis. So you can imagine how this plays out in practice. If you publish a paper and you observe some wild, wacky byproduct, and then you put forward a hypothesis for explaining that byproduct, then forever your name is tied to that particular mechanistic hypothesis. And as the years go on, you continue to see your name in print attached to that hypothesis. And of course, then you hope that hypothesis is right. And you don't really have any incentive to prove it wrong because all you would be doing is proving yourself wrong. On the contrary, you can imagine a system where you delineate all possible mechanistic hypotheses, and then it's a situation where it's like heads you win, tails you win. You delineate the entire explanatory framework for a given set of observations, and then however things play out, you're in a good situation. So that's how, if you only view it from selfish reasons, that's the reason to pursue multiple hypotheses, is that it makes you look good. So this algorithm for truth seeking looks something like this. And I take the time, and Ryan in the boot camp takes the time to outline this, because in the context of this course, organometallic mechanisms sometimes are weird and wacky, and they look dissimilar to things that you're used to as people more comfortable in the S&P blocks. But just because they're weird and wacky, it does not mean that they're wrong. And so having algorithms for truth seeking is highly important in the context of learning and becoming familiar and developing an intuition for the D block. Also, because I think as educators, we also try to think about what are lessons we can communicate that transcend whatever specific domain that we're operating in and can be useful to you as you navigate your career. And I think strong inference is one where, even if you're working in total synthesis, and the context in which you're seeking truth is about distinguishing among 5 different retrosynthetic disconnections for a target and prioritizing which is the best, this is still a very useful algorithm in that domain. So here's the algorithm. First, it's about the observation stage, the piloting stage, where you're exploring the world around you and looking for points that are interesting, points that pique your curiosity, points that are worth exploring in the first place. In the context of organic chemistry and organometallic chemistry, that's often an interesting reactivity phenomenon that we then want to understand mechanistically and design several possible mechanistic hypotheses. That sometimes is not easy. We've been in many times in the group where we think we've covered all possible hypotheses, and then you're talking with the visiting speaker and they propose yet another hypothesis that you haven't entertained, and it's not easy to come up with complete coverage of the possible explanatory universe. But so this is hard work, and the next part is also hard work, designing experiments that rule out specific hypotheses. So in the context of mechanism, this could be a deuterium labeling experiment where you have 4 different possible mechanisms, and each of them would put deuterium at a different position, and you can run the experiment and hopefully obtain a clean result. This too is not trivial. And if in that simplified case where each different mechanism gives deuterium a different position, then you see where deuterium goes, and then that allows you to rule out all the other possibilities. Obtaining a clean result is, I mentioned, not trivial, and we've been in this situation. I'm sure you, as young researchers, have been in the situation where you run what you think is a well-crafted experiment, and you get an outcome that you really cannot conclude anything meaningful from. And that could be, let's continue this thought experiment of a deuterium labeling experiment. Maybe you run that deuterium labeling experiment, but it only gives you 5% yielded product, 95% decomposition, and the label goes 2 different positions. Is that a clean result? Is that an actionable piece of data? Arguably not. So none of these steps are easy, and it looks simple and straightforward when you just, all you have to do is jot it down on a tablet. But to actually implement this and iterate on this and repeat as needed is a real challenge that I think we can all probably do better in the context of our research. And I think hopefully in some of the examples that we cover in class, you'll see both in problems of the day, homework sets, exam, and then some of the literature examples that we cover, you'll see good examples of strong inference, experimental design, and you'll see how this plays out in practice. Okay, so that's the quick primer on strong inference. Now we'll shift gears and I'll provide some general introductory contextualization for the class and how it's organized. And then the bulk of today's lecture will focus on main group organometallic chemistry, which is not a part of the Crabtree, the Hartwig textbook. You'll note that the Hartwig textbook, actually, the title is Organo-Transition Metal Chemistry. So that tells you that there's a heavy emphasis on the D block. Over the years of teaching this class, we've essentially by demand of the student attendees, we've added lectures, added a lecture and then sprinkled content throughout on main group organometallic chemistry, not only because there's a lot of modern work that's interesting, but because often as chemists, synthetic chemists, one of the first exposures we have to organometallic chemistry is making a Grignard or using N-butyllithium to make LDA. And so developing an intuition from main group organometallic chemistry is essential as you move forward as an organometallic chemist in the year 2025. Okay, so quick primer, organometallics lies somewhere at this intersection between inorganic and organic chemistry. Inorganic chemists like to spend their time thinking about cool ligand architectures, cool structures that have extreme properties, that have high levels of bond order, that have low coordination numbers, weird geometries. And often inorganic chemists pursue these intellectual interests in the context of feedstock conversion problems like CO2 reduction or methane to methanol oxidation. As organic chemists, we spend our time interacting with organometallic chemistry, often but not always in the context of catalysis, where we're thinking about molecular complexity generation. And we're really end users of catalytic processes such as decarboxylative couplings, popularized in the Barron lab, MHAT couplings, popularized in the Shenby, Boger, and Barron labs, CH functionalization methods, directed and non-directed, developed in the U lab, among many others. And so where we fall at Scripps on the spectrum is really somewhere here. Let me change the highlight color. This end of the spectrum, or another way people like to talk about this, I just heard this recently, but I think it's pretty good, is as an organometallic chemist, you can be a capital O or you can be capital M. So like the capital M people are over here and the capital O people are over here. So at Scripps, we're mostly capital O type organometallic chemists, which is neither good nor bad, but I'm just trying to paint this landscape for you that there's a lot more out there. And so if topics of ligand design, of topics of electronic configuration, of magnetism, those pique your interest, then that could be a good opportunity for a postdoc. So we're somewhere in this intersection here between where classical principles of coordination chemistry and classical principles of organic chemistry meet. The definition of, I promise I won't spend a lot of time doing boring definitions, but the definition of organometallic chemistry is any molecule containing a metal carbon bond, or more generally, a metal main group element so for example, metal hydrides, metal boreal species, etc. And so as we progress through the class, we'll talk about reactivity in different terms, and it's important to understand the origins of reactivity. There's and this is really just review. There's a thermodynamic component. So when we're talking about things being stable or unstable, and we're talking about ground state stabilization, ground state destabilization, these are thermodynamic descriptors. When we're talking about something being reactive or inert, substitutionally labile, these are kinetic descriptors. In this case, we'll be talking about transition state stabilization or destabilization. And reactivity can have both, can and often does have both components, but it's important to keep them clear in your mind. I try to situate, to the extent possible, situate what can be complex seeming phenomenon into first principles. And I think one that is useful to come back to again and again is electronegativity. One of our guest speakers will be Josh Figueroa from UCSD, and he likes to emphasize this point that electronegativity, Pauling electronegativity that you read off the periodic table, is really a readout of orbital energies. And you'll probably hear that 10 times from him in the lecture. Electronegativity is just another way to talk about orbital energies. This is a great way to rationalize some of the reactivity trends that seem a little bit murky and mysterious in organometallic chemistry. And so just to orient ourselves here, there's some Pauling electronegativities that you're familiar with: lithium, magnesium, aluminum. Whereas carbon on this Pauling scale, 2.55. Fluorine, 3.16, and then palladium, 2.20. So one of the key points here is look how similar the electronegativities of carbon and palladium are. Look how different the electronegativities of lithium or magnesium and carbon are. With that right there, it allows you to predict how organometallic reagents composed of these elements are going to behave. In particular, it allows you to know that in organolithium, in this tug of war for electrons, carbon is going to win out and behave more like a carbanion, and lithium is going to be more like a cation. This is going to have more salt-like character, more ionic bonding character, whereas carbon and palladium, they're equal players in this tug of war. And so a carbon-palladium bond has much more covalent bond character. And right there, from that alone, allows you to have some prediction about what types of functional groups these two reagents might react with. For example, polar functional groups in the case of a very polar reagent, and neutral functional groups in the case of a reagent that has more covalent character. So I realize this is review for a lot of people, but I just can't emphasize enough how important it is to ground when you're to ground things in first principles to the extent possible. All right, let's also orient ourselves in terms of the strengths of the bonding interactions that we're talking about here. A metal-carbon bond is relatively weak compared to the main group element bonds that we're used to encountering, and also weak compared to metal heteroatom bonds. So here we're talking about bond strengths. It varies a lot. It varies, we'll talk about this in the periodic trends lecture. It varies depending on what row the metal is in. It varies depending on the nature of the carbogenic substituent. But there's a big range here, as you can already appreciate. But in general, these are relatively weak bonds compared to the ones that we're most used to encountering. I take the time to explain this because, or linger on this because when we talk about what is the thermodynamic driving force for a reaction happening, it's important to be able to do this inventory of what are the bonds we're breaking, what are the bonds we're forming? Is this actually exergonic or is it endergonic? Okay, we'll jump right in here and feel free to interrupt me if you have questions. We've got a problem of the day coming up where you'll see some of these principles in action. Preparative methods for main group organometallic reagents. The first, and one that you've probably all done, this is, I think, actually like the first organometallic reaction I ever ran in undergrad, grinding metallic magnesium turnings with a aryl or benzylic halide, is oxidative addition. So zero valent metal doesn't have to be zero valent. It could also be +1 oxidation state, for example, but a low valent metal reacting typically with some kind of a electrophile like an organohalide. In this case, if we're thinking this is the zero oxidation state coming in and it's a simple 2 electron oxidative addition, then this would go to the +2 oxidation state. Okay, so I mentioned this point about thermodynamics. So let me linger on this for a second. So here's a reaction that you all are probably familiar with. So what is the thermodynamic driving force of this reaction? I just told you that carbon metal bonds are relatively weak. So where is the thermodynamic driving force from this reaction? Yeah, Kevin.
Precipitation of the salt.
Formation of the salt, and in the case of precipitates, that will provide extra driving force. But Kevin's got it. The formation of the salt, high enthalpy of formation of the salt, is generally what renders the reaction exothermic. So in some cases of metals with high atomic number, the salt that you would be forming, for example, the halide salt you'd be forming is not does not give you as much thermodynamic driving force. So a strategy in that case where you do not get enough compensation of salt formation is to add in the form of alloying. For example, you've probably heard of various amalgams, mercury, sodium amalgam. The origin of the effectiveness of those types of metal precursors is exactly that. In this case, you can still get the thermodynamic driving force of your salt formation while forming a carbon metal bond to a high atomic number. So you get the compensation needed for the weak metal carbon bond formation by making a more stable salt. Renji, would you mind? I've got some printout of notes for myself on the copier. Could you grab that? Okay, let's jump into problem of the day number 1. I'll change the screen share and hopefully this doesn't totally break everything. So admittedly, oxidative addition of metallic lithium or metallic magnesium to an organohalide is not that interesting. That's undergraduate stuff. But what is interesting in this space? You know, one of the things is that is interesting is reactions with classically inert bonds. So, for example, what about carbon fluorine bonds? What about persistent fluorinated polymers or industrial waste bonds? So this example, problem of the day number one, allows us to see some of the modern manifestations of what is classical reactivity. So take a minute or two to sketch this out. We have this interesting diamag. This is an example from Mark Crimmins' group, one of the leaders, young leaders in main group organometallic chemistry. Unusual looking dimagnesium compound. So try to think through, you know, I always like to encourage people, if you are looking at something bizarre that you just haven't come before, try to orient yourself based on first principles. Like, is it nucleophilic? Is it reducing? Is it oxidizing? Is it electrophilic? Try to situate how many electrons this interesting complex has, what its oxidation state is, and then think about in the context of what else we're covering in the class, how's it going to react with polytetrafluoroethylene, i.e. Teflon, with DMAP as the hint here is that DMAP ends up getting incorporated into the organometallic product from this reaction. Okay, so take a minute or two to think about that and then compare notes. And I will then get to pick the very first volunteer of the 2025 class. Oh, that's what I was afraid would happen. Yeah, it's just my notes. Plastic. Yeah, I agree. All right, Al, start us off with some basics here for a warm up. Mes group, give me the structure of a mes group. That's on the ligand here.
4, 6, Benno.
2, 4, 2, 4, 6. Trimethyl. Phenyl. So the groups that you see in coordination chemistry, the common ones are sometimes different than those we see in organic chemistry, so it's worth defining everything. And then this ligand class, if you haven't seen this before, you might recognize its cousin, the ACAC group, acetyl acetanoate. This is a beta diketiminate ligand. So NAC-NAC binds analogously to ACAC bidentate XL ligand. We'll talk about that terminology. Al, what, I know we haven't done oxidation state assignments yet, but
Right, so we need to switch yours.
thanks. Okay, so we've got the mes group defined. We haven't done oxidation state assignment formally, but it is useful to orient ourselves in this case. So what oxidation state is this magnesium?
There's some magnesium 1.
Okay. So we just said that the NAC-NAC is analogous to the ACAC. So here, really what we're doing is just doing charge inventory. We see that the overall complex is charge neutral. We know that the ligand that's binding is anionic. Each one of them is -1. So we've got to have 2 plus charges. That means each magnesium is going to have 1 + 1 charge. And so that's just a primer. We'll, again, if you don't, we'll talk about this formally in a moment, but that just helps us orient. We know that the happy oxidation state for magnesium is +2. So +1 is not looking particularly happy. So that gives you an idea of, okay, this thing probably wants to give up electrons. It's probably reducing. Okay, Al, take us home here.
So when I see DMAP with dimers, I kind of think that it helps in breaking dimers by coordinating to the metal. Does that happen here?
Okay, that's reasonable. So you're gonna break this up, but that's probably not gonna be the final product.
Yeah.
I'd imagine. So then what's gonna happen? Okay, so you want to have DMAP here. Isn't gonna, sorry, I have to do this.
DMAP there. Then I think there's an open coordination side. And the final product might be square planar magnesium.
So Al's saying there's this open coordination site here. Doesn't look super happy. Give us a little more to work with. Al.
Can you do a direct oxidative addition?
Ah, okay. So if you were to do, sorry, I'm struggling a little bit here. So if you were to do direct oxidative addition, I guess you're thinking about, if I'm understanding you correctly, you're thinking about one of these carbon fluorine bonds. So that would mean that you're gonna oxidatively add, and I'm just gonna abbreviate this as RF. So you oxidatively added to that perfluoro fluorine bond. Okay. Is it happy like that? 5 coordinate magnesium 2, magnesium 3.
So there's a part of me that says that the ACAC-like ligand might be labile enough to become monodentate, but I think the
What
guess
about this
it's probably
group?
cause of that
Does this
might
look happy to you?
no, would
Is
you
this happy with
get
its place in life?
one complex is magnesium fluoride and then the other is a alkyl magnesium?
Okay, so now you're on to, so clearly the magnesium fluoride bond formation is providing a lot of driving force here. So you correctly picked out that what I drew was unhappy. Now, to think that it's fully unimolecular might be an oversimplification because it's bimolecular magnesium 1, there's very likely going to be some kind of bimetallic character to the oxidative addition. We'll cover different mechanisms for oxidative addition later. All we asked in this question is to figure out the magnesium-based product. What would be formed as the byproduct in this case. So it's pulling out effectively 2 fluorines. From the Teflon, giving an alkene byproduct. If this were just simple hexafluoroethane, then you'd generate tetrafluoroethylene as the gaseous byproduct. And that's computationally how this was modeled. But this is the isolable organometallic byproduct. Yeah.
Is it more XAT-like mechanism or is it the
Well,
opposite?
that's a good question. I mean, fluorine is not the best XAT halide.
But the
So there's a,
formal
yeah, I would,
is also not happening.
I think the mechanism, mechanistic details, I would say are not totally clear. I would direct you to the original reference where most of the mechanism in this Jack's paper from 2 years ago was explored through DFT, through a model system. So again, this is not a run-of-the-mill example. It's magnesium 1, which if you struggle with that, you can just kind of view it as one equivalent of magnesium 0 and one equivalent of magnesium 2, and that's effectively how it reacts. The magnesium 0 as the bond splitting. There's a, you can think of it as like a E2 or a kind of base mediated type metal fluoride elimination as the next step. And then it just dimerizes to form the more stable halide bridged adduct. Again, a theme that we'll see again and again is that halides like to bridge to give stable dimeric multimetallic adduct.
Do we have beta fluoride elimination?
Do we have one?
Beta fluoride elimination.
Right, so this could be considered a beta fluoride elimination.
Then we can argue that kind of Sanford-Ritter oxidative addition of directly go to the CF bond and then just beta fluoride elimination to give the same product.
Yes, isn't that what I was saying? Oxidative addition and then beta elimination?
Yeah.
Yeah, okay. Yeah. thank you.
Magnesium 1 suggests allosphere single electron transfer and then eliminate.
Well, but it's not, the Teflon is not a very good electron acceptor for that type of mechanism. So that would be my pushback. That, and I think in the paper, maybe Annabelle can correct me if I'm wrong, they have a more concerted mechanism proposed than a SET mechanism.
Sorry, Kieran.
Yeah.
You think of it just as like, do you have to have dimer breakup? Couldn't you like take one electron from the magnesium bond and another electron on the magnesium center, do oxidative addition with that, and then you still have a magnesium 1 with that one electron left from the magnesium bond. So like kind of like metathesis, like you use the magnesium bond to oxidatively insert into the.
Yeah. So we'll cover this in the context, not so much of main group elements, but in the transition metal series of mechanisms for bimetallic oxidative addition or bimetallic reductive elimination. So that's directly analogous to what you're proposing, and that's totally based on the information you have. That would be a totally plausible way to think about it. Okay, so now we'll talk about, so again, we're in this theme of how to make organometallic compounds, and this category is referred to in terms of the nomenclature taxonomy. They call it exchange. I kind of think of it everything I'm going to show you as different forms and flavors of transmetallation. So transmetallation just means that a ligand on one metal is getting transferred to another metal center. And there are a lot of different manifestations of transmetallation. Again, it's called exchange here. I would normally use the term transmetallation to describe pretty much everything I'm going to show you here. So one manifestation of this is we can think of it as a redox transmetallation. It's a zero valent metal. So think here like magnesium turnings and then a preformed organometallic that you're adding to that. So think here like an organolithium or zinc dust plus an organolithium. And then in addition to swapping the carbogenic ligand, the metal is undergoing some kind of redox change that I realize now is not specified here. So let's say this is in the zero oxidation state, and this is going to the +1 or +2 oxidation state, and this metal is getting reduced. Again, thermodynamics are a key consideration. What is the driving force? And this can be read out by the relative stabilities of the carbon-metal bond that you are forming here. And again, that goes back to principles of electronegativity. Another manifestation is the organometal to organometal or metal exchange version. So you can think of two different organometallics here swapping partners. And then one that is, I won't say too much more about this. C on this list, I think, is one that's very commonly encountered in the context of cross-coupling catalytic cycles, where the carbogenic group of one organometallic or organometalloid is transferred to another metal center. So think here in the context of a Suzuki Miura coupling, this would be your organoboron, and it's transferring the aryl group to the palladium 2 hydroxide or chloride adduct that's formed after oxidative addition. The key consideration here is that, again, the salt that you're forming is stable. So in the case of, again, let's continue on this example of a Suzuki Miura coupling. If we're forming a boron oxygen bond or a boron halide bond, you're transferring that very electronegative atom, the hydroxide or the halide, to a very electropositive metal that can form a strong bonding interaction, ionic bonding interaction. Okay, next type is organometal plus organohalide, which we would also call metal halogen exchange. Again, something many people in the classroom would likely have run before. So think about your generations of organolithiums or Grignards for synthetic purposes. Again, a lot of these reactions are implicitly or in principle reversible. And so the kinetic barrier is often low. And so the question is just, where does the equilibrium shift? And shifting the equilibrium depends on the nature of the bonds you're breaking and the bonds you're forming, no surprise there. And in this case, which of the two R groups is superior in stabilizing negative charge? So let's see an example that some people in the group would, in the class would have run before. T-butyllithium plus aryl halide, say aryl iodide, aryl bromide, to get your aryl lithium, and T-butyl halide as byproduct. And often in practice, these reactions are run with two equivalents of t-butyllithium. Maybe someone can chime in very quickly, volunteer for why that is. So many volunteers. Oliver.
So the byproducts, the fission butyl bromide,
Yeah.
get alkylated, or our old species can add into that. So if you use a second equivalent, you can eliminate the bromide and liberate isobutylene gas.
Let's draw this out
Sure.
in fully for full clarity. So you have this enticing looking beta hydrogen. You have an extra equivalent now of base. It's going to pull off this proton. Going to give you, I think you said, isobutylene as a byproduct. And your properly clear. Now your lithium X salt and those are your byproducts. And because gas formation here is going to be irreversible, this will provide your by Le Chatelier's principle, this will pull your equilibrium far in the towards the right. So in terms of this trend I noted before, the equilibrium shifts farther to the right in this order here. So depending on the orbital hybridization, some hybridizations are better than others at stabilizing negative charge. The SP with higher S character, and the general trend is higher S character leads to better ability to stabilize negative charge. So SP is more stable than SP2, is more stable than SP3. Again, something you would have learned in undergraduate organic chemistry. In practice, lithium halogen exchange only works for iodo and bromo arenes. Occasionally for chlorines, chlorides, although not that well, and never, I shouldn't say never, almost never for aryl fluorides. Does anyone want to comment on why that is? Yeah, Alex.
Just with making benzynes. Upon ortholithiation.
We have an Al and an Alex, sorry.
Oh, sorry, yes.
No, you're good, you're good. Alex, you can get the next one. So you were saying, I think, Al, I heard you. Here, there's a couple things going on. So now fluorine is very electronegative atom, so it's holding its electrons in orbitals of low energy. So what can happen, and it has the effect also of acidifying protons ortho to it. So you can imagine here, and I think this is what Al said, is that you have a higher kinetic barrier for organometallic generation. You also have now an acidified ortho CH bond. So rather than undergoing lithium halogen exchange, this would prefer to form benzyne. And that's often a competing process in these metal halogen exchange with worse leaving groups. Mechanisms for metal halogen exchange still hotly debated, I will say. And you can view this as lying on a continuum, and I've sort of mapped out two limiting scenarios here. One is the SET radical type mechanism, where within the solvent cage, you have electron transfer to generate free radicals that then recombine to swap partners. The other is more of a 2-electron mode, where the key difference is formation of this 8 complex. So an 8 complex, you'll hear this terminology again, refers to a chemical entity that is anionic and typically coordinatively saturated. So think boronate complex in the context of a Suzuki coupling zincate complex. So here you have your carbanion effectively at, engaging with the halide to generate overall negative charge and then decomposition of that heat complex. The boundaries of which of these pathways is operative is still not well defined, so I won't comment too much more about it, but just to know that these are two limiting scenarios, the 2-electron mode, the 1-electron mode, depending on the metals and the carbogenic groups involved. Other pathways for generating organometallic compounds with main group elements. This one should be pretty familiar. Deprotonation, you have something that's a CH acid. It doesn't even have to be that acidic, to be honest. So it doesn't have to be a malonate or something of that pKa. Even arenes, particularly electron-rich arenes, can undergo this soft type deprotonation. For the mechanisms that have deprotonative character, though, it is important that the metal be alkali in character and that the CH bond be acidic. So there, again, there's a spectrum of reactivity, how hard or soft this CH to CM swapping is. And here's the kind of limiting extreme of more of a soft type CH to CN swapping with mercuric acid. Mercury has this beautiful suite of reactivities, unfortunately has associated with it terrible toxicity. So you typically aren't using this in 2025, but does all sorts of interesting things, including with aryl CHs can undergo this, what could be viewed as analogous to a CH activation to make organomercury compounds. And we'll see organomercury compounds come back in the context of cross couplings as playing a really important role, central role in Richard Heck's early work to develop Heck-type alkynylations. Okay, let's swap over to problem of the day number 2 to see some of these organometallic reagents in action. Okay, problem of the day 2, there are 2 parts to it. The first asks, and if for those of you who attended Andy Thomas's lecture, you will have a good head start on this question, I would say that. If you didn't, then good luck. The activity of N-butyllithium decreases upon storage in THF for a few hours. Explain why. And part B asks you to expound upon the mechanism that you're going to put forward in part A and think about why you're drawing what you're drawing and how to achieve different pathway selectivity. Okay, this should be a relatively quick one, so I'll just give 30 seconds for you to think about it, and then I'll call on a volunteer.
I just want to continue.
All right, Alex, I feel like you got left out last time, so I should call on you this time. So get us started here. What's going on?
So N-butyl is gonna get directed by the oxygen lone pair to depromate the adjacent CH bond.
Good. Actually invoke this kind of dative stabilizing interaction if you like. The byproduct here is butane, 1, 2, 3, 4. And then what?
The lithiated THF breaks up into ethylene and the lithium unilated acetaldehyde.
Okay, we'll leave it to everybody to think about mechanistically how to push arrows. Give this product, but Alex said ethylene plus lithiated acetaldehyde. Of course, ethylene is a gas, so you would see some bubbling take place and be concerned if this was happening. All right. So let's stay with you, Alex. You anticipated part of question B, so the origin of site selectivity, one explanation would be directivity from the lone pair of oxygen. Now, let's say we didn't want to lithiate at position 2, how would we go about achieving? I mean, there's only one other position, so how would we lithiate it at C3 if we so wanted?
Probably just need to saturate the coordination sphere of lithium so you can add something like HMPA.
Ah, okay. I'll have the structure of this drawn on the sheet if you're not familiar with it. So add HMPA, and I think you said this is going to coordinate as a ligand to the metal. It's a relatively strong Lewis base, so that would break up oxygen's ability to direct potentially. And so that would get you to C3 lithiation. And then what happens from here? Here, you're whispering.
Just
Eliminate.
eliminate the homoallylic alcohol.
Okay, so we've got effectively an anti-Baldwin type 5-exo trig, 5-endo trig, 5-endo or exo? 5-endo trig, thank you. And you said that would eliminate to the olefin. Okay, and the way these are read out practically is these are trapped with some kind of if you want to follow reaction progress, you can track this one. Okay, and that brings us to here's an original reference for this, if you would like. That brings us to our chemist of the day. Does anybody recognize this individual?
Before we move on, could I ask a question about this?
Yes, of course.
Instead of HMPA, could you go at it a bit differently by saturating THF with lithium chloride prior to the addition so that the coordination of O with lithium sort of disrupts your initial coordination with N-butyl lithium? Or are they in equilibrium enough that you can still get?
That's interesting. I mean, you have then this added complication of what the chloride is going to do to the reactivity of the organolithium itself. I'm not sure. I don't know that they ran that experiment in this paper, so I could only speculate on what the outcome would be. But I think your rationale is sound. You just have to do the experiment. Chemist of the day, any takers? Aha. From the UK system, Oliver.
It's Jonathan Claydon, it's at the University of Bristol. He does total synthesis, he does methods, he does work on feature isomerism, planar chirality, and
Dynamic Foldomers, born in Uganda, educated at Cambridge with Stuart Warren, and then postdoc with Mark Julia of Julia olefination fame, and is the author of this paper on reversed metallation, reversed selectivity metallation induced by HMPA. Thank you, Oliver. Okay, that just springboards us right into problem of the day number 3. So here's HMPA for those, as I promised, there's the structure. And this one will be out of Andy Thomas's lecture. So again, you have a good head start if you attended that lecture. The question reads, T-butyllithium exists in its monomeric form in THF at -78. But if you're not happy with something that smokes and sparks upon exposure to air and want something even more reactive, you can get a more reactive form by adding HMPA. So how does it, and the hypothesis is something called a separated ion pair. So take a minute to speculate on what the structure is of this separated ion pair and then how you get there via intermediate 3. All right, Ningxi, what do you think here?
If you form a dibutyl lithium anion.
Okay, I hope I drew this out ahead. Oh, yes, okay, there we go. I
Oh,
wanted
there
to
it
give
is.
myself a head start, so I didn't struggle to draw this in front of you. There we go. All right, so we're following Alex's reasoning and also the kind of concept that Pierre mentioned. We're coordinatively saturating one of the lithiums with the strongly Lewis basic HMPA. So the way this is coordinating is you've got these very Lewis basic lone pairs that are coordinating data interactions. You've got tetracoordinate lithium surrounded by HMPAs. That leaves the T-butyl anion without a home, and it finds another lithium. I think that's what you proposed. And then what happens next? Ningxi.
How about illumination?
An elimination.
Because I see the.
Yes, kind of. You probably wouldn't call it an elimination, but let's just call it a dissociation. So I think you're thinking this is going to dissociate. And you've got this now carbanion. Something like this. Is that what you had in mind? And this is, what's the name they use? Separated ion pair. So here you have ions, they look pretty separated to me, separated ion pair. Is that structure, I have that right, Benji?
I think the authors claim that you just need to generate really small amounts, like the reservoir is probably on the far left side. Pure lithium, really active lithium species, but just after you generate this very small amount of separated ion pair, this just reacts very differently from what you would expect for turbulent lithium. Like they demonstrated, you can selectively lithiate not the proton right next to the oxygen of a chromate. So it's quite impressive. You can read the paper.
Did they manage to observe the turbulent anion? Because I remember they had NMRs for the diturbulent lithium anion, but not the one on the right.
Yeah, they do have NMR evidence for the one that's on the left, and they have a hypothesis that it's the one.
Do they have NMR evidence for just turbulent anion on its own?
No, I believe, not in their publication, because it's generated in too small amount. Not really detailed.
But they could find triplet on there?
Yes, that's NMR characterized, and the characterization was done at, I think, minus 115 degrees Celsius.
It's also the middle one.
Yeah,
This one is called a
Not in oil, we talked about.
triplet ion pair. Separated ion pair. Good. Okay. Cute. All right, we'll go rapid fire here, try to stay on schedule. So still continuing this theme of how to make main group organometallics. We talked about oxidative addition, we talked about metal halogen exchange, transmetalation. With some of the metalloids, boron, aluminum, silicon, germanium, zirconium, common strategy is to get at them through addition to a pi bond, and this foreshadows something we'll cover in quite a bit of detail, which is migratory insertion, of which hydrometallation is one subtype. So some of you will have probably done this. You take Schwartz reagent and add it across an alkene or alkyne to make a new organo-zirconium reagent. Likewise, you can transfer a carbogenic group in this step in a process called carbometallation. So take, for example, trimethyl aluminum that would undergo methyl alumination. But for some reagents, let's take this one, not AR, that would be dibol, diisobutyl aluminum hydride. You have a competition. You have the ability to migrate H or the ability to migrate the carbogenic substituent. And which would you expect to be preferred? H. Amy, why H?
I think it's smaller, it's easier, or in the middle, hydrogen bond.
Sterics, okay.
Yeah.
Perfect. So the key upshot, do not use dibol and hope for carbo illumination. That will undergo hydro illumination. Okay, another one here, and this is a little bit out of fashion, or no, sorry, I'm getting ahead of myself. So another one that is you see from time to time as carbene insertion, either free carbene or metallocarbenoid into the element H bond of a silane, of a borane. So in the most simple manifestation, you take diazomethane, heat or irradiate to generate a free carbene, which then can undergo SiH insertion to make a new organosilicon compound with extrusion of N2 gas. And then again, here, this is where I was saying I was getting ahead of myself. These are methods just for completeness I will cover, although to be honest, these have fallen a little bit out of fashion. Again, in the theme of organomercury, compound synthesis, mercury dichloride plus some kind of metal carboxylate salt that undergoes salt metathesis to make the mercury carboxylate. Upon heat that extrudes CO2, sort of a poor man's decarboxylative coupling to make a new organomercury halide or diorganomercury. And then likewise, the same logic can be applied for diazonium synthesis, diazoniums as an input to organomercury synthesis with extrusion of N2. Okay, so some of that chemistry covered at the end is probably not what you're going to do on a day-to-day basis, but just want to understand those general reactivity trends because those will be important moving forward. So let's talk about structure. So the theme here is that these structures are complex, highly bridged, monometallic, or sorry, a multimetallic in most cases, hard to draw. So this puts your chem draw or your freehand draw skills to the test. Some of this, again, if you went to the Andy Thomas lecture, you would have seen this covered. So oftentimes in solution and in the solid state, these are oligomeric. So let's take N-butyllithium as our first example to cover. We draw it out as this nice, innocent looking linear compound. In practice, depending on the solvent, this is exists in various aggregation states. In ether, it's tetrameric. So I've drawn this in a way where each of the black dots represents a lithium. Each of the faces is an N-butyl group. So an equivalent way to represent that is this cubic structure where alternating vertices are black and red. Or this structure here. In lower dielectric constant solvents, it aggregates further still to a hexameric form. Again, where each vertex is a lithium and each face is an N-butyl. And the bonding on each of the faces is a 4-center 2-electron bond. So 3 metals, 1 carbon group sharing 2 electrons. These clusters then interact with each other, and that leads to low volatility as well as low solubility. So these can crash out solution. Let's consider the case of phenolithium here, and we'll introduce some terminology, that of mu. So what does mu mean? Mu means that the atom in question or the group in question is bridged. The number that's in superscript denotes how many different metal centers that group bridges. So phenolithium is mu3 when in its etherate form, meaning it bridges 3 lithium centers in, again, an analogy to what we talked about before. Upon coordination of TMEDA, we often hear about TMEDA being used to break up clusters. What does that mean with a little bit more granularity? Well, here you can see up treatment of the mu3 cluster with TMEDA leads to a lower bridging state, mu2. And the resulting mu2 dilithium adduct is isostructural to hexaphenyl dialuminum. And isostructural is a term, isostructural and isoelectronic, as well as isolobal are 3 terms that we use to describe different coordination complexes that have similar bonding, electronic configuration, or frontier molecular orbital picture, respectively. The picture can get more and more complicated. So with CP lithium, so CP is cyclopentadienyl anion. Really important ligand in coordination chemistry that can coordinate a number of different ways, but in this case is coordinating in a so-called 8-to-5 fashion with all 5 atoms of carbon interacting with each lithium in an infinite solid state 1D polymer. This term of sandwich complex is often used to describe organometallic complexes that have 1 metal with 2 flat organic ligands. And so this can be, if that's a sandwich, then this could be viewed as like an infinite Big Mac. Meat, bread, meat, bread, meat, bread, add infinite. Make sure to take note of that, infinite Big Mac. Got to do America proud, right? Okay, let's cover this and then we'll wrap things up. So organomagnesium complexes again, we draw them when we talk about using a Grignard, we typically will represent it in this form. But what's really going on in solution? It's more complex than this. So the Schlenk father and son research duo originally outlined what is now called the Schlenk equilibrium, shown in the gray box here. And they appreciated that the organic groups on a Grignard can actually swap partners. And so you can populate this diorganomagnesium as well as the magnesium halide states. Now, how to get from here to here, and is this an actual representation that's consistent with reality and solution, is another question. So there's a nice review of this topic in this JPhysChem paper that I would refer you to. But let's just take a minute as we wrap up the class to draw this out. So the hint here is that magnesium likes to be tetrahedral or tetracoordinate and tetrahedral. So what might this actually look like in solution? Let's take a representative, we'll just use solvent, generic solvent S. I'll try to draw this in 3D form so you get a little bit of a sense of the three-dimensional structure. And so when it's bridged like this and drats. My gosh, what's going on here? When it's bridged like this, then you get a clearer sense of how the adjacent magnesium centers can communicate with each other. And it can give you appreciation for the fact that they're in close enough proximity where the ligands can swap. This is effectively a transmetallation, you can view it that way. And so you can get two organic groups per one magnesium. And you can then the two solvents on the other, and you can appreciate, because in terms of this electronic tug of war, now you have two carbogenic groups on one magnesium center and two halides on the other. These less electronegative carbogenic groups are getting increasing increasing delta minus compared to the version where the ligands are equivalently distributed. And so this diorganomagnesium is indeed, as you might expect, a more reactive form. And that leads to this question then of how could you populate that and use that as a synthetic tool? So if you take, but you have to be a little careful here. If you populate this diorganomagnesium state and you're not careful, you can get these infinite polymers that, as you can imagine, are insoluble, will crash out, these polymeric 3-center 2-electron bonds. You can keep the magnesium monomeric if it's bulky, and then the solvent that you're in will dictate the overall speciation. So in ether as solvent, you can maintain this tetrahedral solvate structure as shown here. And you can think of the ether as almost your like ligand on the metal. So if you want to tune reactivity, for example, you can switch to alternative solvents like THF, to methyl THF, which gives you an added boost from ground state destabilization. And the last thing I'll cover here and wrap things up, sorry, I went a little bit over because of the technical difficulties, is this thinking back to the Schlenk equilibrium. So what if we want to populate this state a common trick in synthesis is to use dioxane. So what might we expect dioxane to do if we were to take a Grignard in solution, add dioxane? And I told you empirically it was observed that this drives the equilibrium in this direction. Why might that be the case? Amy,
Dioxane will coordinate and it'll precipitate out, like what Kevin was saying,
what will precipitate out?
the dioxane magnesium adduct
Which magnesium adduct?
of the X.
Okay.
MgX.
The magnesium dihalide salt forms a stable, so you can imagine this is nicely set up to make a coordination polymer. This will indeed crash out. That allows you, through Le Chatelier's principle, to populate the diorganomagnesium adduct. And if we apply this, then Amy, to this cute example, what would the byproduct be treating this digrignard with dioxane?
Wait, is it an alkyl bridging? That would distinguish to one magnesium.
A magnesium cyclobutane. Interesting 1,3 bis nucleophile. And then, okay, this is actually it. So that you've also heard about turbo-Grignards. Turbo-Grignards are an even more reactive form of Grignard that are, and this was popularized by Paul Nochel, who I think in German sometimes they call Knockel. Nobody knows whether to use American pronunciation, German pronunciation, French pronunciation. It's all different. Turbo-Grignards rely on addition of lithium chloride salt. And so if we just apply exactly what we just learned, what we might expect to form in solution here are these. And actually, this is not so dissimilar to Pierre's proposal from earlier in the class in a way. Pierre inspired solution here. So this is the aggregate structure that's generated in solution. And now the last question I'll ask for today is, why would this be more reactive? Why would the carbogenic group be more nucleophilic in this flavor of Grignard to earn the name turbo as compared to classical Grignard structures where instead of lithium, you have a magnesium there? Yeah.
The chlorides.
What's your name? Sorry, I don't think we've met before. Eugene.
The chlorides acting as electron withdrawing groups to make the dipole moment of the R G bond greater.
That's a good point. Yeah, so I think you're saying you've got like more, but those would all pull at this electronic tug of war. They would pull electrons out of the carbogenic. They might be homo lowering, actually. But I like this idea of thinking about what's pulling and pushing electrons. So let's consult back to our handy dandy electronegativity chart that I started the lecture with. And we'll note that lithium has an pulling electronegativity of 0.98, magnesium 1.31. So you have a more electropositive element here in lithium, which means it's not really fighting hard for its electrons, which means you get added delta minus in the carbogenic group, homo raising, more nucleophilic. Okay, sorry to keep you a little bit over today. We'll wrap things up here and see you all on Thursday. I think the TAs and I will stay after for a minute if you have any questions. Everybody.